transition rate for absorption from an initial electron state psi I, so perhaps down here in the valence band somewhere, with energy EI, so here's the energy of that first state, to a final state, psi F here, perhaps it's up in the conduction band, with some energy EF. And for the moment, we don't know anything about the relation between possible k values down here and k values up there, although we will figure out a very simple relation between the possible k values. And we're presuming we've got an oscillating perturbation of angular frequency omega. And then from Fermi's golden rule, we know that the transition rate should obey this expression. We have delta functions here that we will handle later on, but we know that the transition rate is proportional to the modulus squared of this matrix element. The delta functions will disappear from the mathematics once we consider very dense sets of possible initial and final states, and we certainly have such dense sets in the case of some semiconductor bands. In this Fermi's golden rule expression, then, Hp0 is the amplitude of an oscillating perturbation that's oscillating in this case at some angular frequency omega, and that could just be an amplitude here, such as Hp0, times a cosine omega t, or as we prefer to write it, the sum of two complex exponentials here. Now, this would be a reasonable form for the perturbing Hamiltonian. This would be our usual electric dipole form, and in that case, we're saying that the electric field specifically is in the z direction, and the magnitude of the energy associated with this interaction between the electric field and the electron is the electronic charge times the field times the position coordinate of the electron. We are also now interested in the spatial variation of this amplitude of oscillation here. And in general, since we're dealing with an electromagnetic wave, there will indeed be some spatial dependence of the electromagnetic wave. Explicitly, we'll allow for that by allowing this perturbing Hamiltonian amplitude here to vary with position r. And how explicitly it varies we'll get back to later on, but for the moment we have to allow it to vary with position. The matrix element here in Fermi's golden rule we could now write out explicitly as an integral. It's just another way of writing this expression here with our initial and final wave functions. And we're explicitly now allowing Hp0 to vary in space because the electromagnetic field at some angular frequency omega will indeed vary in space. Now, though we could continue here with the electric dipole version of the perturbing Hamiltonian, as we've written it out here, the electronic charge times the field times the position, we can connect somewhat better to other semiconductor phenomena if we switch instead to writing the perturbing Hamiltonian in terms of this rather strange electromagnetic concept of the magnetic vector potential. And in that case, if we follow through the electromagnetism, instead of this expression here, we'll obtain an expression, at least approximately, which is like this. This is the magnetic vector potential associated with the electromagnetic field. M0 is the usual free electron mass, and P here, with a hat on it, is the momentum operator, minus IH bar times the gradient. Note, incidentally, that both electric and magnetic fields can be deduced from the vector potential A. This switch to the vector potential form of the electromagnetic field may look a little intimidating. The vector potential is famously a somewhat difficult idea to understand in electromagnetism, and first introductions to electromagnetism will often avoid even introducing it, using just electric and magnetic fields instead. Now, whether the vector potential has a simple physical meaning or not in ordinary classical electromagnetism is in the end not very important, at least not to us here. However, it turns out to be mathematically a very compact way of writing down electromagnetism, and advanced discussions of electromagnetism typically use it. For those of you used to vector calculus, the magnetic field is basically the curl of the vector potential. And in one way of discussing this, the electric field is in part related to the time derivative of the vector potential. In classical electromagnetism, with some approximations neglecting higher order terms, we get to a specific important result. The energy associated with the interaction of a charged particle with mass with an oscillating electromagnetic field can be written classically in this A dot P form, though it takes some algebra to derive this. For our purposes here, we can mostly ignore the details of the vector potential. It's true in general that the vector potential approach is slightly more correct because it includes not only the electric field effects, but also the magnetic field effects. For the problem of optical absorption in semiconductors, it would in practice make no actual difference to our calculation if we stayed with the electric dipole way of writing down the perturbation. However, the use of the magnetic vector potential means that when we make the switch from a classical to a quantum mechanical energy expression, or Hamiltonian, we end up rewriting the perturbing Hamiltonian using the momentum operator rather than the position operator. As a result, we're going to end up using momentum matrix elements, and those matrix elements connect to many other behaviors in semiconductor materials. Here, to be clear, we are not yet quantizing the radiation field itself. This vector potential A is representing a classical field. All we are doing is writing down the perturbing Hamiltonian in a way that will allow us to connect somewhat more directly with other aspects of semiconductor theory, because we will have results written in terms of this momentum matrix element. In all other respects, the results we get here would be essentially the same quantum mechanically if we had just stayed with the electric dipole perturbing Hamiltonian. So now we're going to write the vector potential of a wave at frequency omega in the following form. So this is our magnetic vector potential, and K optical in here, K op, is the wave vector of the optical field inside the material, and we take the field to be linearly polarized with its electric vector in the direction of a unit vector E here. So now this E is a unit vector. It's not the electronic charge, it's just a unit vector in this particular problem that is polarized along the direction of the electric field. So we see here in this expression that we have propagating waves, one with I k optical dot r minus omega t, and the other with the complex conjugate of that, minus I k optical dot r minus omega t. So this is a real field because it's a sum of something plus its complex conjugate, but we prefer to work with this complex exponential form here. So this is just a way of describing a propagating electromagnetic wave, in the present case expressing it entirely in terms of vector potential. Now, in this expression, we are only going to keep the term in e to the minus I omega t here. So that will be this term. And that's because we know from our previous discussion of Fermi's golden rule that this term corresponds to absorption rather than emission. So the spatial part of our perturbing Hamiltonian is only this part here. And the total perturbing Hamiltonian is that spatial part times the exponential of minus I omega t. Now, at the moment, this appears perhaps a somewhat ad hoc assumption. When we later on come back and properly quantize the electromagnetic field, we'll see exactly how to deal with this a bit more rigorously. But for the moment, we make this simple assumption, which does turn out to work, that we're only going to keep this e to the minus I omega t term here in the time variation of this field that is still being expressed classically as an electromagnetic field. We're not yet quantizing the electromagnetic field, which is what would give us photons, by the way.